Hello, folks. Well, last time we were looking at abstract data types and language support or enforcement for the idea of ADTs. Now we want to move on and look at some of the same ideas with an OO focus. So, thinking about object-oriented languages, right, at the start of the year, we looked at, or at least very briefly talked about, the three major paradigms as kind of an imperative style, the C style of programming, the functional style, and the object-oriented style. I'm suspecting folks should be pretty familiar with both the imperative style and the OO style from a practical standpoint, since you've been using it for a few years by now. The functional viewpoint we took a good look at in the first half of the course. So what I want to do now is focus on kind of the relevant key points from a programming languages perspective for the OO paradigm. So obviously we're looking at the idea of a bunch of interacting objects, right? Some means of defining objects, each of which has their own fields and methods, where the object's methods access its fields. Communication is handled by some form of communication between the objects. So typically we talk about this in terms of method calls, but any kind of message passing can work, right? Anything where one object can say to another object, hey, I need you to do this, and here's the information I want you to process for me. Now, we've talked about pure and impure languages with respect to paradigms. Again, from an object-oriented sense, in a pure OO language, everything would be an object. There'd be nothing that was a standalone function, nothing that was a primitive data type that wasn't an object. And as with the functional languages that we looked at, there are relatively few languages that are truly pure. So most of them are going to represent a hybrid of some sort, to some different degree. Right, in C++, you've obviously got a very distinct hybrid there, since you have support for objects, but you can also completely happily use standalone data types and standalone functions. So it is very clearly and obviously a hybrid. Java is much less so. Probably still regard it as a hybrid, since you do still have some primitive data types that don't need to be represented as objects. But again, there's different points along the spectrum of hybrid, and it's something you want to be aware of when you're looking at a language. There are a few languages that do treat everything as objects, where you've got a relatively pure approach, Smalltalk, Ruby. There are a few others, but again, just keep in mind that most languages are going to go with some kind of a hybrid, simply because developers like having the ability to draw from 2 or 3 different paradigms to do what they want to do. Now, in terms of features, obviously for an OO language, you've got to start with the notion of an abstract data type, where you've got an encapsulation of some data and some operations on it, and you've got this idea of the public interface that you use for your communication between objects, and then some kind of hidden implementation behind the scenes, right? How does the inner details of the object actually work? Then we add inheritance, where objects can inherit fields and methods from ancestors. Right? So you derive one class from another, from another, from another. And at different points within that, they might actually go through and override the fields or methods that they've inherited with their own versions of that field or that method. And then the last thing that we'll take a look at with respect to the OO features that we're interested in is the idea of dynamic dispatch, where when we call a method on an object, we figure out at runtime which real method needs to be called, rather than figure that out at compile time. And we'll get into some examples and some detailed discussion on that in just a couple of minutes here. So looking at inheritance first, again, you should all be pretty familiar with the use of this by now. And the idea is it allows us to have kind of a top-down design of our data hierarchy or object hierarchy, much like we use a top-down design for the functionality of our programs. Right now we've got a top-down design for our data. And as we take our objects, essentially each layer of inheritance is giving successively greater specialization. Right? You've got a fairly abstract item at the top, and a little bit more specialized at the next layer, and a little bit more specialized below that, and a little more specialized below that. right? So you're just gradually adding more and more detail, more and more granularity. And when you need to use a specific object, you pick the one that's at the right level of granularity for what you're trying to do. And this improves our modularity, our abstraction, our ability to reuse code, the maintainability, right? All of the same ideas that we talked about in terms of abstract data types apply here, possibly more so. Now, there is the possibility that you've got some marginal loss of time and space efficiency because you are adding extra administrative overhead to maintain these objects and to maintain the communication between them. But most modern OO languages and compilers are pretty good at optimizing the handling of our OO features. In terms of the inherited fields and methods, it's possible we'll add features for restricting access to the things that we have inherited. So if I inherit things from a parent class, I might want to restrict how much of that gets passed on to classes that are derived from me, classes that inherit from me. Again, we might want to be able to override the things that we've inherited, right? Provide a new localized, specialized version instead of the ones that we inherited from our parent classes. Some languages are going to provide support for multiple inheritance, where I can inherit directly from a bunch of completely different classes, right? C++ is an example of that. So there are a variety of different inheritance features that we should be thinking about. And what we'll look at in the next video will be consideration of how some of this stuff actually gets implemented when we want to make our language work. So if you're thinking about turning this into assembly language somewhere down the road, what happens? How do we do this? So the other thing we wanted to spend a little bit of time on was this idea of dynamic dispatch. The idea that when we call a method on an object, we want to figure out at runtime what the right method is, not try and figure that out at compile time. And again, the idea is if I've got this hierarchy of classes where the parent class defines a method and then the child class overrides that and the grandchild class overrides that. If I call a method on an object, I want to know that I'm calling the right version of the method for the object that I'm dealing with. So a nice quick and easy example here is suppose I've got a method buried deep within my code someplace where I'm passing that method an instance of a parent class. I'm saying you're going to expect to receive a parent class, and we'll call our parameter x. And within the function, or within the method rather, we'll call foo on x. So presumably the parent class has defined method foo. Now suppose we've got a child class derived from that, and maybe a grandchild class derived from that, and they each override foo with their own version. Now, somewhere else in my code, if I actually have an instance of my child class, and I call that method f on it, so I pass my child class instance c off to method f, then f is going to run foo on c. So we're going to have a c.foo taking place somewhere along the line. Now, should that call the child class version of foo, or should that call the parent class version of foo? If we're thinking about static dispatch, where the compiler has to make up its mind at compile time which version of foo to call, you're almost certainly going to say it's got to call the parent class version, right? The compiler at compile time would look at this and say, this is an instance of parent class, you're calling foo on it, use the parent class version of foo. But if we're using dynamic dispatch, where we wait until runtime to figure out which one we should call, well, we pass an instance of the child class, it gets in here and says, I've got a child class instance of this. I should probably use the child class version of foo. And that's the distinction between dynamic dispatch and static. It's just whether we wait until runtime to figure out which method to call. Now, of course, that means that the compiler, to achieve this, would have to stick in code so that when a method call is made, it can actually figure out what kind of a class I've been passed and which is the right method to call. So we'll get into looking at implementation issues associated with this in our next video.